Welcome to Domain 3 of the CCSP Exam Cram Series, 2023 edition, covering every topic mentioned in the official exam syllabus for Domain 3 of the CCSP exam. As a cybersecurity strategist and a VCSO for a regional bank, I can tell you firsthand, you're going to use the skills that you learn in the CCSP Exam Prep Series every day of your cybersecurity career. And more importantly, last year I helped hundreds of thousands achieve cybersecurity certifications like Security Plus, CISSP, and now I'm bringing that same formula to the CCSP exam. This installment represents the third video in the series of 6, one for each domain of the CCSP exam. When we wrap the series, I'll release a consolidated full course video. Domain 3 focuses on cloud platform and infrastructure security. And as always, I recommend the CCSP Official Exam Study Guide from Cybex, which includes 1,000 practice questions, a couple of practice exams, and some flashcards to help in your study. And you can find the link to the least expensive version out on Amazon.com in the video description. And to help in your preparation, a PDF copy of this presentation is available in the video description. I've also included a clickable table of contents in the video description so you can jump forward and back in the video as you need. So let's get into Domain 3, Cloud Platform and Infrastructure Security. As always, I will cover every topic mentioned in the official exam syllabus. I'll also provide examples of concepts wherever I can to give you some additional context. And as in Domain 2, I'll also do a bit of show and tell in a real cloud environment. Again, the CCSP is CSP agnostic. It doesn't focus on any one cloud platform, but I do find a bit of show and tell in a real environment gives you some context for those areas where maybe you don't have any experience in your work life yet. So let's have a look at a few exam essentials applicable to Domain 3, those areas the official study guide promises will factor significantly on exam day. We have risks associated with each type of cloud computing. Essentially, more services generally equals more risk, and more control over your environment means more risks you are responsible for mitigating. It goes back to that shared responsibility model we first talked about in Domain 1, and we'll touch on here again in this session in multiple respects. Explain key business continuity terms like RTO, RPO, and RSL. If you are not familiar with these acronyms, you will be by the time we're done with this session. These are key concepts that help set the bar for your business continuity plan and disaster recovery plan requirements. Responsibility sharing between customer and provider, so essentially who is responsible, customer or CSP, in each area of cloud infrastructure. We'll talk about design and description of a secure data center. We'll look at the build versus buy decision, physical and environment design considerations, and the pros and cons in each area. Business continuity and disaster recovery in the cloud. That's similar to on-premises, but there's certainly more complexity in the agreements between the cloud customer and the cloud service provider. I will add that these exam essentials are my rough mapping from the official study guide, because the fact of the matter is the exam essentials and the book chapters themselves in the official study guide do not map one-to-one to exam domains. You'll notice there are more than 6 chapters in the book because some domains are covered in part across each of multiple chapters. So let's jump into 3.1, Comprehend Cloud Infrastructure and Platform Components. We'll touch on several areas of infrastructure and platform here, including physical environment, network and communications, compute, virtualization, storage, and the management plane. Now, in the shared responsibility model, customer and CSP share security responsibilities. So in each area, we will review responsibilities and security controls and who owns them. So you can imagine in a cloud scenario, we'll talk a bit less about the physical environment because that physical data center is entirely the domain of the cloud service provider. We will talk about how you can do your due diligence on ensuring that your cloud service provider is designing and managing that data center effectively. So let's start with a talk about the physical environment. So there are infrastructure components that are common to all cloud service delivery models. Most of those components are physically located with the CSP, but many are also accessible via the network. So the CSP is taking on customer data center facilities, infrastructure, and management responsibilities. They are responsible for the physical by and large. In the shared responsibility model, though, we know some elements of operation are shared by the CSP and the customer. Just a reminder for the exam, you want to know who owns which roles, who is responsible for what from that shared responsibility model. So if we think about it from a physical perspective, the CSP owns all aspects of physical security in their data centers. They own it down to the wire, the facilities, the equipment, the environment, and the personnel that care for that physical infrastructure. But the CSPs utilize common controls to address these risks. So for physical security standard measures like locks, security personnel, lights, fences, and visitor check-in procedures, just as we do in our own data center. Logical access controls like identity and access management, single sign-on, multi-factor authentication, and logging, so they have an audit trail. And controls for data confidentiality and integrity, just as any cloud customer would, but with much broader controls. So let's look at what I mean by broader controls in the form of an example. So for example, ensuring that communication lines are not physically compromised by locating telecommunications equipment inside a controlled area of the CSP's building or campus. So physical security, that would be broader control. It protects data integrity and service and resource availability for that matter. So let's move on to network and communication. We'll start with IaaS, where we know the customer is responsible for configuring VMs, the virtual network, and guest OS security. But the CSP is responsible for the physical host, physical storage, and the physical network. Moving into platform as a service, the CSP is responsible for the physical components, the internal network, and the tools. It's cheaper for the customer, but the customer has less control if you remember that diagram. In the SaaS model, the customer remains responsible for configuring access to the cloud service for their users, as well as shared responsibility for data recovery. The CSP owns physical infrastructure as well as network and communication security. So let's break it down another way. So if we just look at those three models, we'll look at IaaS first, where we know that the customer is responsible for configuring the VMs, the virtual network, and the guest OS security as if the systems were on premises. The CSP provides the tooling to secure the VM, but the customer must configure those tools. And the CSP is responsible for configuring the security of the network, the storage, and the software for the physical host. The CSP owns all physical security here. Moving into PaaS, where we know that the CSP is responsible for everything from the IaaS model, all the physical components. They are also responsible for internal network and tooling. The customer is responsible for configuring the application and data access security. Any additional customer control is generally provided through service SKUs or service tiers. And what I mean by that, for example, in a PaaS web application context, for example, you'll find some service tiers may give a customer their own physical host or access to greater compute capacity, but they have to spend to get that greater control in the form of a different service tier within that PaaS service. So moving on to software as a service, where the customer remains responsible for configuring use access to the service. They are configuring access control for their users. The customer also has shared responsibility for data recovery. Now, what do I mean by that? Well, the CSP may provide tools for recovery, but the customer may need to perform recovery themselves in some cases. Perfect example, in Office 365, users have access to hundreds of previous versions of a document available for self-service recovery right there from within Microsoft Word or PowerPoint, but the user must perform that recovery themselves. Next, we have compute, the infrastructure components that deliver compute resources like our VMs, disk, processor, memory, and network resources for customers. So how does the CSP manage compute capacity? Well, reservation is one way, a minimum resource that's guaranteed to a customer. You'll see that in the form of a VM SKU, for example. Limits, maximum utilization of compute resources by a customer. That's handled through a VM SKU. We can set a minimum and a maximum. Limits are allowed to change dynamically based on current conditions and consumption, remembering that a CSP is going to oversubscribe their infrastructure by design. And shares, a weighting given to a particular VM used to calculate percentage-based access to pooled resources where there's contention. And you'll even see VM SKUs that allow us to select a lesser SKU at a lesser price for non-production workloads where we know we're going to be deprioritized in times of contention, but we pay less for that resource over the course of the month as we're paying for that subscription. In case of a shortage, though, host scoring will determine who gets capacity, generally speaking. But what we see in those VM SKUs is that we can choose inexpensive SKUs that get deprioritized and have low resource limits, or expensive VM SKUs that give us very high resource guarantees. So in each delivery and service model, the CSP remains responsible for the maintenance and the security of the physical components of compute. They are dealing with that physical host and that physical storage and that physical network. The customer remains largely responsible for their data and their users, but between the physical components, there can be quite an array of software and other components. So who is responsible for each of these remaining parts varies by service and delivery model and sometimes by the CSP. The details should be spelled out in the contract and you want to be familiar before you enter into a production workload scenario. The CSP also deals with the challenge of multi-tenancy, and we could argue that customers deal with multi-tenancy in their own private clouds, but those multi-tenant customers are all internal customers, generally speaking, where the CSP is dealing with external customers with signed contracts, so it's certainly a stickier situation. But let's shift gears and talk about virtualization responsibilities and risks. So the security of the hypervisor is always the responsibility of the CSP. The virtual network and the virtual machine may be the responsibility of either the CSP or the customer. It depends on the cloud service model. And there are risks associated with virtualization you should be familiar with. A flawed hypervisor, for example, can facilitate inter-VM attacks. Network traffic between VMs is not necessarily visible, so bad actors posing as customers could certainly carry out attacks of their own if we don't have the right network controls in place. Resource availability for VMs can be impacted. Now, we talked about how the CSP can prioritize resource allocation, but we still have that lingering worry about noisy neighbors, those neighbors that are sharing our physical infrastructure and always consuming maximum capacity. And VMs and their disk images are simply files. They can be portable and movable. So if the CSP doesn't have the right controls in place, we could fall prey to a different sort of malicious insider attack if they don't have their own separation of duties and access controls in place to limit access to those files. So let's talk through security recommendations for the hypervisor. Installing updates to the hypervisor as they're released by the vendor, of course. Restricting administrative access to the management interfaces of the hypervisor. Capabilities to monitor the security of activity occurring between guest operating systems. The VMs, essentially. And then security recommendations for the guest OS. So again, installing all updates to the guest OS promptly. Backing up virtual drives used by the guest OS on a regular basis. Those hypervisor recommendations are all the responsibility of the CSP. The security recommendations for the guest OS are customer responsibility, though the CSP may provide tools to facilitate ease of patching and backups. So the CSP's hypervisor security includes preventing physical access to the servers, limiting both local and remote access to the hypervisor. And the virtual network between the hypervisor and the VM is also a potential attack surface. Responsibility for security in this layer is often shared between the CSP and the customer. These components include the virtual network, virtual switches, virtual firewalls, virtual IP addresses. The responsibility is going to vary by model, whether it's IaaS, PaaS, or SaaS. And when I say hypervisor in this case, just to make sure we're crystal clear, we talked in Domain 1 about the hypervisor types. We have the Type 1, which is the bare metal hypervisor. That's VMware ESXi, Microsoft Hyper-V, KVM, dedicated host, no operating system in the middle. Whereas a Type 2 hypervisor is hosted on a guest operating system. That would be VMware Workstation, Oracle VirtualBox. So Type 1 is that production scenario hypervisor. Type 2 is much more common in development and test scenarios. So we're always talking about a type 1 hypervisor in this case. And again, the CSP is always responsible for security of that physical host and the hypervisor running there. Now, there is a virtualization-focused attack called out in both the official study guide and the common body of knowledge I wanted to mention, and that's VM escape. This is where an attacker gains access to a VM and then attacks either the host machine that holds all the VMs, the hypervisor, or any of the other VMs. Or a malicious user breaks the isolation between VMs running on a hypervisor by gaining access outside their VM. Now, VM escape is generally preventable. One protection would be ensuring patches on the hypervisor and VMs are always up to date. We do know that the CSP is responsible for patching that hypervisor. Who's responsible for the VM depends on the model. We know that the customer is responsible in the IaaS model for patching and backing up their VM. The CSP can also ensure guest privileges are low. They have server-level redundancy in place, as well as host-based intrusion, prevention, and detection. So let's shift gears and talk about storage. So cloud storage has a number of potential security issues. Various types of cloud storage are discussed in Domain 1. We're going to touch on some of the highlights here in terms of risk. So data spends most of its life at rest, so understanding who is responsible for securing cloud storage is very important. Now, CSP responsibilities include physical protection of data centers and the storage infrastructure they contain, security patches and maintenance of the underlying data storage technologies and other data services they provide. On the customer side, properly configuring and using the storage tools. We know that sometimes the CSP is responsible for giving us tools potentially, but the customer must configure and use those tools. And then logical security and privacy of data they store in the CSP's environment. So I want to unpack customer responsibilities a bit further. I mentioned CSPs often provide a set of controls and configuration options customers can use to secure the use of their storage platforms, but they may need to make some specific configurations beyond the default. So the customer is going to be responsible for assessing the adequacy of these controls and properly configuring and using the available controls. Access over public internet, VPN, or internal networks, for example. As I actually showed you in Domain 2, in the world of cloud storage, when we're looking at a storage account, your CSPs often give you the ability to block internet access altogether, to force TLS security for data in transit, and to limit access from internal networks. But you have to use those controls as a customer. Ensuring adequate protection for data at rest and motion is based on the capabilities offered by the CSP. Feature configuration, key management would even be a customer concern if the customer is managing their own keys. And configuring secure access, whether that's private or public. At the end of the day, when you're looking at a cloud service provider's storage account they've issued to you, the data is generally going to be encrypted at the account level at rest, but you have a number of additional configuration options to restrict access. But the bottom line here is in the cloud, the customer loses some control over storage. They lose control of the physical medium where the data is stored, but they retain responsibility for data security and privacy. So how can customers deal with their challenges and responsibilities without control of the physical storage medium? Because after all, the inability to securely wipe physical storage and the possibility of another tenant being allocated the same previously allocated physical storage space is a definite concern. Our logical storage account sits on a physical storage medium somewhere, and the customer retains responsibility for secure deletion in spite of that lack of control over the physical medium. And that's where compensating controls come into play. For example, only storing data in an encrypted format. As we saw in Domain 2 in some of our show and tell, the cloud storage account was encrypted by default. We had the option to add another layer of encryption called double encryption. And a customer can choose to retain control of the keys needed to decrypt the data, so not allowing the cloud service provider to hold those keys. Together, these permit crypto shredding when data is no longer needed, rendering any recoverable fragments useless. So let's talk about the management plane. So what is the management plane exactly? Well, it provides the tools, the web interface, and the APIs necessary to configure, monitor, and control your cloud environment. It provides virtual management options equivalent to the physical administration options a legacy data center would provide. So we can power VMs on and off, provision new VM resources, migrate VMs, just as a few examples. You interact with the management plane through tools, including the CSP's Cloud Portal, PowerShell or other command line, or even client SDKs. Now, this is separate from and it works with the control plane and the data plane. So let's talk about these two for just a moment. The control plane is what you're calling when you create top-level cloud resources, such as with ARM or Bicep in Azure, CloudFormation in AWS, or even Terraform. Infrastructure as code is what I'm talking about here. And the data plane performs operations on resources created through that control plane. Essentially, management plane control equals environment control. So let's talk about securing the management plane. So the key interfaces we're worried about include the Cloud Portal, the main web interface for the CSP platform, the Azure Portal, AWS Management Console, the Google Cloud Console. From a scheduling perspective, our ability to stop or start resources at a scheduled time, we have tools available like the Instance Scheduler or Lambda in AWS, Azure Automation or Azure Functions on the Microsoft platform, and then orchestration, automating processes to manage resources, services, workloads, and infrastructure as code deployments. CloudFormation in AWS, Azure DevOps on the Microsoft platform, Cloud Build in Google Cloud Platform. And then we have our maintenance functions, updating, upgrading, security patching, etc. We can secure all of the above in the same fashion across these platforms. We secure management plane interfaces with multi-factor authentication, role-based access control, and role management. Next up is 3.2, design a secure data center. Here we'll talk through logical design elements like tenant partitioning and access control, physical design elements like location selection and the build or buy decision, environmental design, heating, ventilation, and air conditioning, and multi-vendor pathway, and then what the syllabus calls design resilience, so building resiliency into design. And since the CSP is responsible for design of the physical data center, we'll talk about how customers can do their due diligence to ensure that the CSP's physical data center design decisions are adequate. So we'll start with logical design, where I expect more focus will be given on the exam. And the logical design of a data center is an abstraction. In the now legacy co-location scenario, customers were separated at the server rack or cage level, so it's a physical isolation. In a logical data center design in the cloud, customers utilize software and services provided by the CSP. And the logical design of the cloud infrastructure should create tenant partitioning or isolation, limit and secure remote access, monitor the cloud infrastructure, and allow for the patching and updating of systems. The CCSP exam focuses largely on tenant partitioning and access control, which are called out in the syllabus. So we'll take a look at both of those. So in the cloud, logical isolation and CSP multi-tenancy makes cloud computing more affordable, but it creates some security and privacy concerns in the process. If isolation between tenants is breached, customer data is at risk. Multi-tenancy is a concept that was developed decades ago, though. Business centers physically housed multiple tenants. Co-location data centers supported multiple customers, but their isolation was in many respects physical, and the risk in these scenarios is largely physical. It's a server, rack, or cage isolation. In the public cloud, tenant partitioning is largely logical. Customers are sharing capacity across the CSP data center, including the physical components. CSP and tenant share responsibility for implementing and enforcing controls that address the unique multi-tenant risks of the public cloud. In this scenario, access control is a primary, if not the primary, concern. A single point of access certainly makes access control simpler. It facilitates monitoring through an audit trail, but any single point can become a failure point as well. In the hybrid cloud, which is very common in large organizations, a single login for on-premises and cloud can simplify identity and access management, a very common identity model. One method of access control is to federate a customer's existing identity and access management system with their CSP tenant. Another method is to facilitate identity and access management between cloud and on-premises using identity as a service. A couple of examples of identity as a service would be Azure Active Directory used in Office 365 or Google's Cloud Identity used with Google Workspace. There are multiple local and remote access controls available, including Remote Desktop Protocol, the native access protocol for Windows operating systems, as well as Secure Shell, which is the native remote access protocol for Linux and Unix operating systems, and very common for remote management of network devices as well. And RDP and SSH both support encryption and MFA in their modern versions. Now, Secure Terminal or console-based access is a system for secure local access. In the legacy co-location scenario, we would commonly see a keyboard video mouse or KVM system with access controls to limit console access in a scenario where multiple customers have physical servers in a single shared rack. You could actually rent rack space without committing to a full rack, and that would be coupled with oversight from the colo data center staff to ensure that one customer didn't touch another customer's physical server in that rack. Jump boxes, a bastion host at the boundary of lower and higher security zones. Your CSPs offer this as a service in some cases. We have Azure Bastion and AWS Transit Gateway as a couple of very popular examples. Virtual clients, software tools that allow remote connection to a VM for use as if it is your local machine. Virtual desktop infrastructure, or VDI, for contractors is very common in this scenario. So let's take a look at physical design, starting with the build versus buy decision. Building your own data center from scratch and buying an existing facility each have their advantages and disadvantages. So let's compare build versus buy. Build requires significant investment to build a robust data center that has the resiliency we need. Buying that capability is generally a lower cost of entry, especially in a shared scenario. The build option offers the most control over data center design. So buy has less flexibility in service design because it's limited to what the provider offers. The build option requires knowledge and skill to match the quality of the buy option. In the buy scenario, we know someone with a high level of skill, generally speaking, is designing that data center. Shared data centers do come, though, with additional security challenges. The fact of the matter is CSPs offer many advantages of the build option at a buy price tag. Customers can leverage the CSP's experience to get that build level quality and near build level flexibility, but at a buy cost of entry. So in physical design, location selection is one of the first decisions. So availability of affordable, stable, resilient electricity is important. Natural disaster exposure needs to be considered. Are we exposed to flood, hurricane, tornadoes? Availability of high-speed redundant internet connectivity, as well as other utilities. Add, say, propane, natural gas, and diesel to run your generators. Physical site security, so securing against vehicular approaches, bollards, gates, visibility. Location relative to existing customer data centers, so business continuity, disaster recovery considerations. And geographic location relative to customers. And when you move to the public cloud, most of these are CSP decisions. A customer just chooses which CSP regions they're going to reside in. And you need to know the challenges of physical security belong to the CSP. A strong fence line of sufficient height and construction, lighting of facility perimeter and entrances, video monitoring and alerting, electronic monitoring for tampering, visitor access procedures, so guest access, for example, with controlled entry points. Interior access controls, badges, key codes, secured doors, fire detection and prevention, protection of sensitive asset systems, wiring closets, etc. Due to its cloud focus, the CCSP exam spends little time on physical security, but focuses more on the aspects of logical security and design. It is a fact that there is no security without physical security, but in the cloud, this is a CSP responsibility. I will, a bit later in this session, though, show you how you can verify that your CSP has taken the appropriate steps to build excellent physical security into their data center design. Now, you may see questions on the exam around the data center tier standard, which lays out a 4-tier standard for data center availability and uptime and redundancy. So availability and uptime are often used interchangeably. There is actually a difference. Uptime simply measures the amount of time a system is running. Availability encompasses availability of the infrastructure, the applications, and the services that are hosted. It's generally expressed as a number of 9, such as 5 nines, 99.999% availability. It should be measured by the cloud customer to ensure the CSP is meeting their SLA obligations. These tiers come from a company called the Uptime Institute. This is an organization that publishes specifications for physical and environmental redundancy expressed in these 4 tiers that organizations can implement to achieve high availability. So let's take a look at each of these tiers, starting with Tier 1, which is basic site infrastructure. This involves no redundancy and the most amount of downtime in the event of unplanned maintenance or an interruption. It must have a UPS, an uninterruptible power supply that can handle brief power outages as well as sags and spikes in power. It must have dedicated cooling equipment that can run 24/7 and a generator to handle extended power outages. The expected availability of Tier 1 is 99.671%. Moving into Tier 2, we have redundant site infrastructure. This provides partial redundancy, meaning an unplanned interruption will not necessarily cause an outage. It adds redundant components for important cooling and power systems. Facilities must also have the ability to store additional fuel to support the generator, and it's expected to provide 99.741% availability. Tier 3, concurrently maintainable site infrastructure, adds even more redundant components. It has a major advantage in that it never needs to be shut down for maintenance. Enough redundant components that any component can be taken offline for maintenance and the data center continues to run. It's expected to provide 99.982% availability. And then finally, we have Tier 4, fault-tolerant site infrastructure, which can withstand either planned or unplanned activity without affecting availability. This is achieved by eliminating all single points of failure. And it requires fully redundant infrastructure, including dual commercial power feeds, dual backup generators, and is expected to provide 99.995% availability. Heating, ventilation, and air conditioning, or HVAC, is also a concern because an HVAC failure can reduce availability of computing resources just like a power failure. Customer reviews of a CSP should include review of the adequacy and redundancy of their HVAC systems. Now, I mentioned that the physical aspects of security and the physical aspects of data center design belong to the CSP, but also that I'd show you a way that as a customer or on behalf of your customers, you can validate, you can do some due diligence to ensure that CSP has made good decisions in their data center design. And one of those documents is the SOC 2 Type 2 report. Now, because of the confidential information in a SOC 2 Type 2 report, some CSPs will require a non-disclosure agreement prior to sharing, or at least that you are a customer. And a routine review of the most current SOC 2 report is a critical part of a customer's due diligence in evaluating CSPs. So let's unpack that SOC 2 Type 2 report. What is that exactly? It is part of the Statements on Standards for Attestation Engagements, which is a set of auditing standards issued by the American Institute of Certified Public Accountants. And SSAE 18 is an audit standard that enhances the quality and the usefulness of System and Organization Control, or SOC, reports. So they're designed for larger organizations like cloud providers because the cost of a Type 2 report can run $30,000 or more. They're not inexpensive. Now, the SOC Type 1 report assesses the design of a security process at a specific point in time. So it's looking at your processes at a point in time, a snapshot. SOC Type 2, on the other hand, assesses how effective those controls are over time by observing operations for 6 months. And it is that Type 2 report that we're interested in. So what I'd like to do now, just to give you some context, is show you how to retrieve a SOC 2 Type 2 report from a CSP. And we'll start with Microsoft. I'm here at servicetrust.microsoft.com, their Service Trust portal. And you'll notice here under Certifications, Regulations, and Standards, they show us some of the certifications with which Microsoft Azure and other cloud services Microsoft offers comply. I'll click on All Documents, which takes me to the list of documents that I can retrieve related to certifications. And if I go down the list, way down here under SOC, I will find a number of SOC Type 2 reports. So you see there is a SOC 1, here's a SOC 2 Type 1, SOC 2 Type 2. And if I just click on one of these, what you'll find, I mentioned these are available but often considered sensitive. If I click this to download, you notice here I'm prompted to authenticate. You must be a customer. And incidentally, if you sign in and go a couple of steps further, you'll be prompted to agree to an NDA. Now I've pulled up one of these reports just so you can see what you get. It's a PDF that goes line by line through the SOC requirements with those details. So out of respect for that NDA, I'll stop there. And I'm going to just mention that AWS, similar path to get that SOC 2 Type 2 report. You'll see here they post on their blog when those reports are available, and it mentions we can go to the AWS customer portal, the AWS artifact in the AWS Management Console, and in fact that will prompt us for authentication, and we'll get to those reports. So fairly similar. And another area we need to be concerned with is multi-vendor pathway connectivity as another element of environment design. So connectivity to data center locations from more than one internet service provider is what we call multi-vendor pathway connectivity. Using multiple vendors is a proactive way for CSPs to mitigate the risk of losing network connectivity. And a best practice for CSPs or data centers is dual entry, dual provider for high availability. That means two providers entering the building from separate locations. And likewise, customers should consider multiple paths for communicating with their cloud vendor. So if a customer has site-to-site connectivity with a VPN, building some redundancy into that connectivity. In the end, this protects availability, whether we're talking about the CSP and their two providers, two paths, or that customer to CSP connectivity. And finishing out 3.2, design resilience. So resilient designs are engineered to respond positively to changes or disturbances like natural disasters, or even man-made disturbances for that matter. A few examples of resilient design. High availability firewalls, whether that's active passive or active active. Multi-vendor pathway connectivity that we just spoke about. A web server farm behind redundant load balancers. A database cluster like a Windows or a Linux cluster feature. Service level resiliency requires identifying single points of failure throughout a service chain. So if we're thinking about an end-tier application, resilient design means we're looking at the application layer, any middleware, at the data tier on the back end, and thinking about resiliency in the systems and facilities that surround that application's service chain. And that brings us to section 3.3, analyze risks associated with cloud infrastructure and platforms. Here we'll talk about risk assessment, identifying and analyzing risks, cloud vulnerabilities, threats, and attacks, and we'll finish up section 3.3 with a look at risk mitigation strategies. So risk management on the whole is so important because it's the practice of mitigating and managing the risks to our sensitive data and to our business critical systems. Careful selection of CSPs is important, as is development of service level agreements and our contractual agreements. So when we look at the cloud, the service level SLAs are pretty well established. We do have a responsibility as a customer to make sure that we monitor and hold our CSP to account, but SLAs can also factor when we think about vendors in our supply chain, for example. Organizations can balance cost savings with risk by building a system on top of IaaS or PaaS rather than utilizing a SaaS solution. Bearing in mind that if we go that IaaS route, as a customer, IaaS means more control, more responsibilities, and ultimately more risks that are our responsibility to mitigate and manage. Customers need to be proactive in addressing their responsibilities under the shared responsibility model and making sure that their CSP does the same. And that last point is important because even when a CSP cloud service of one form or another doesn't meet its mandated contractual SLA, it doesn't mean every CSP is going to proactively give you a partial credit in response to that SLA breach. I've seen CSPs that have a major outage and they come back and provide a partial credit to customers due to the SLA failure. I've seen others that definitely do not. Identifying risks is the first step in the risk management process. And to identify risks, we first need to identify the organization's valuable assets. Once we have identified our assets, then we can identify potential causes of disruption to those assets. There are actually some risk frameworks that can provide us with processes and procedures and give us a more systematic and consistent approach. One of those is ISO IEC 31000, Risk Management Guidelines. Another comes from NIST, SP 800-37, which is a guide for applying the risk management framework to federal information systems. And while NIST guidance is applicable to government information systems, you're definitely going to find guidance in there that's equally applicable in commercial businesses. Now, I want to talk about another aspect of risk assessment called out in the official study guide, and that is quantitative risk assessment, which assigns a dollar value to evaluate the effectiveness of countermeasures. Quantitative risk assessment is objective. It ensures our controls are cost effective. In other words, that our countermeasures are not more expensive than the impacts themselves. And risks specific to cloud environments should be identified when we're making a decision to use a cloud service. We should assess that risk before we take that step into that cloud service. And analysis is our next step. Analyzing risks continues the conversation we started by asking what could go wrong. And it seeks to answer two primary questions. What will the impact be if that situation occurs, if the potential impact is realized? And that's what we call the single loss expectancy in quantitative risk assessment. That's expressed as a dollar value. And how likely is that impact to happen? That's what we call our annualized rate of occurrence. So how frequently is it going to occur? That would be expressed as a decimal. So for example, an impact that happens twice a year has an annualized rate of occurrence of 2. An impact that happens once every 2 years has an annualized rate of occurrence of 0.5. And an impact that happens once every 5 years is 0.2. So by those numbers, you can guess that a risk that happens once a year would have an annualized rate of occurrence of 1.0. And with these two figures, with single loss expectancy and the annualized rate of occurrence, we can calculate our annualized loss expectancy. Annualized loss expectancy is the possible yearly cost of all instances of a specific realized threat against a specific asset. So I'd like to look at this with you in the form of a simple example. And we'll at that point calculate our annualized loss expectancy. The formula is single loss expectancy times annualized rate of occurrence equals annualized loss expectancy. So let's just step through an example. We have a scenario. A tornado may strike one of our branch offices once every 5 years, causing a 30% loss to a $1 million building. So we'll begin by calculating the cost of a single occurrence. So what will be the impact if that goes wrong? Well, the single loss expectancy we express as a dollar value. How significant will the loss be? That's our exposure factor. We express that as a percentage. The formula for that single loss expectancy is the asset value times the exposure factor. So doing the math, if we have $1 million building, we have an exposure factor of 30%. That means we expect a $300,000 loss in a single incident. So that's our percentage loss, that exposure factor. So 1 million times 30% or 0.3 when expressed as a decimal is a $300,000 single loss expectancy every time a tornado hits that building. Now let's calculate our annualized cost, our annualized loss expectancy. We said our single loss expectancy is $300,000. Our annualized rate of occurrence Once every 5 years is expressed as a decimal as 0.2. So let's calculate our annualized loss expectancy. We have the $300,000 single loss expectancy. We take that times our annualized rate of occurrence, 0.2, equals an annualized loss expectancy of $60,000. That's that 300,000 single loss expectancy spread across the 5 years for every single occurrence. And that is a simple example. I won't try to tell you that simple example is really simple, but you now have the PDF that you can download with this video, so you can watch this video over and again and look at those formulas and commit these to memory. I'm not certain you're going to see a lot of quantitative risk assessment on the exam, but since it's called out in the official study guide, I want to make sure that you are prepared for exam day. So analyzing our CSP risks. So when we're analyzing a CSP or a cloud solution and the associated risk, it's going to involve many departments and focus areas. Our business units will likely get involved, vendor management, our supply chain potentially, our privacy specialists when we're dealing with risks that involve data breach or data leaks, and our information security department, the folks responsible for securing our cloud infrastructure. And CSP operations should also be considered, but most major CSPs are audited for ISO IEC 27001, 27017, and 27018. Now, what are those exactly, do you ask? Well, these are standards to guide CSPs in their preparation or for customers evaluating potential CSPs. So ISO IEC 27001 is a framework for policies and procedures that include legal, physical, and technical controls involved in an organization's risk management processes. But the focus is on policies and procedures. Then we have ISO IEC 27017, which is a standard developed for cloud service providers and users to make a safer cloud-based environment and reduce the risk of security problems. And then ISO IEC 27018, which is the first international standard about the privacy in cloud computing services. Now, we actually covered ISO IEC 27017 in depth in Domain 1 in Section 1.5. We will cover ISO IEC 27018 a bit later in this series in Domain 6 in Section 6.2. Repetition is good for memorization. I'm going to call these out in various facets throughout the series, so you'll be ready on game day. And CSPs like Microsoft and Amazon do provide resources that demonstrate their compliance with standards like ISO IEC 27001, as well as the 27017 and 18 standards. So we're going to revisit in the Microsoft example here the Service Trust portal at servicetrust.microsoft.com, and I will search for 27017, and what I'll find here are documents demonstrating compliance for various Microsoft cloud services with ISO 27001, 27018, and 27017, all in a single document in the example of that cloud service. And you'll find similar resources in the AWS Management Console. Again, a cloud agnostic exam, but I just want you to understand what your recourse is as a customer or a consultant to customers when you want to verify that your CSP or prospective CSP meet your quality bar when it comes to compliance with well-known security standards. Continuing with risk analysis, let's look at a couple of CSP risks. And risks with a cloud solution are mainly associated with data privacy and information security. There's authentication risk, so does the CSP provide a solution, or is this a customer responsibility? We talked about federation versus identity as a service a bit earlier in this session. So if it's customer managed, we have more control. If it's CSP managed, we're transferring some of that risk over to our cloud service provider. Then data security. How a vendor encrypts data at rest, the strength of the cryptography, and the access controls that prevent unauthorized access by cloud service personnel and other tenants. So some controls may be on by default, but the customer may have to enable others. We saw this in Domain 2 when we looked at cloud storage, where we saw encryption at rest enabled by default. We saw that forcing encryption in transit, so TLS encryption was a feature we needed to turn on, as was double encryption, which would facilitate crypto shredding down the road. Supply chain risk management, so evaluating vendor security policies and processes. Now, most CSPs don't allow direct auditing of their operations, due in part to the sheer number of customers they support. Instead, they provide standardized reports and assurance material regarding their security practices, such as a SOC 2 report, ISO 27001 certification, and specialized reports for regulated data, like HIPAA, FedRAMP, and ISO IEC 27017 and 18. And you saw exactly how we retrieved those standardized reports in one example demonstrated earlier in this session. So let's shift gears and talk about common cloud risks. Now, one risk that's been discussed is the organization losing ownership and full control over system hardware assets. Careful selection of CSPs in the development of SLAs and other contractual agreements are critical to limiting risk. Organizations can balance cost savings with risk by building a system on top of IaaS or PaaS rather than utilizing a SaaS solution. Remember, the service model affects the level of control. But regardless of which deployment or service model is used, some risks are common to all cloud computing environments. So, geographic dispersion of CSP data centers. If the cloud service is properly architected, the disruption at one data center should not cause a complete outage, but customers must verify the resilience and continuity controls in place at the CSP. Downtime. Resilience for network disruptions can be built in multiple ways, such as multi-vendor connectivity, zones, and regions. We discussed these earlier in this session, as well as in cloud shared considerations in Domain 1. Compliance. Compliance data in some jurisdictions cannot be transferred to other countries, so data dispersion is inappropriate. Now, your major CSPs have compliance-focused service offerings, so you'll have some mitigations enabling you to control data residency. Then there's general technology risk. So cloud systems are not immune to standard security issues like cyber attacks, and CSP defenses should be documented and tested, and customers should be aware of their configuration responsibilities, remembering that some security features are enabled by default and others must be configured by the customer, and it's customer responsibility to know which and to be aware of which. Let's shift to risk types. So we have external risks, different threat actors ranging from competitors and script kiddies to criminal syndicates and state actors. Capabilities will depend on their tools, their experience, and certainly their funding. Other external environmental threats like fire and floods, and man-made threats such as accidental deletion of data or users. Internal threats, a malicious insider, a threat actor who may be a dissatisfied employee, like someone overlooked for a promotion. Another internal threat is human error, which is when data is accidentally deleted. CSPs also face these risks, and customers have to verify their CSP has addressed them or provided tools to help customers address them. But customers should know who is responsible for configuration. That's going to be a recurring theme when it comes to security feature configuration. So let's shift gears and talk about cloud vulnerabilities, threats, and attacks. The primary vulnerability in the cloud is that it is an internet-based model. Organizations could be at risk if the CSP's public-facing infrastructure comes under attack. Any attack on your CSP or cloud vendor may be unrelated to you as an organization. Threat actors may be targeting the CSP or another tenant of the CSP. Risks can come from other tenants as well. Customers may be collateral damage of an attack on the CSP. Now I want to talk about cloud-specific risks. The Cloud Security Alliance details the top cloud-specific security threats in their list titled the CSA Egregious 11. and they cover the top 11 threats from year to year. So a recent list included data breaches, misconfiguration and inadequate change control, lack of cloud security architecture and strategy, insufficient identity, credential access and key management, account hijacking, insider threat, insecure interfaces and APIs, weak control plane, metastructure and applistructure failures. We'll talk about those two terms if you're not familiar. Limited cloud usage visibility, and abuse and nefarious use of cloud services. So let's break these 11 down a bit further. First, we have data breaches, which are loss of sensitive data due to a security breach. Now, an unintentional loss or oversharing is a data leak. A data breach is loss due to a security breach. You'll want to know the difference for exam day. Misconfiguration and inadequate change control. Software can offer the most secure configuration options, but if it's not properly set up, then the resulting system will have security issues. The same is true of any cloud service. We can remediate this risk through change and configuration management, a deliberate written plan that goes through a review process to reduce errors. Lack of cloud security architecture and strategy. As organizations migrate to the cloud, some overlook security or they fail to consider their obligations in the shared responsibility model. Insufficient identity, credential access, and key management. It's important to remember that the public cloud offers benefits over legacy on-premise environments, but it can also bring additional complexities. Identity and access management, encryption, and secret and key management are different than on-prem and essential in the cloud, but we need to spend time in architecting those solutions to make sure we're following best practices for the cloud, so we modernize our approach to these areas as we modernize our approach to compute and service delivery. Account hijacking, credential theft, abuse, and/or elevation to carry out an attack. Phishing is actually the most common approach to account hijacking. Insider threat, disgruntled employees, employee mistakes, and unintentional oversharing. Job rotation, privileged access management, auditing, and security training are all potential mitigations. Insecure interfaces and APIs. Customers failing to secure access to systems gated by APIs, web consoles, and the like. Controls like multi-factor authentication, role-based access control, and key-based API access are all controls that can help mitigate these threats. Next, we have weak control plane issues, weaknesses in the elements of a cloud system that enable cloud environment configuration and management. This would be our web console, our command line interfaces, and our APIs. The good news is most CSPs offer reference architectures to ensure customers secure and isolate their dev, test, and prod environments as well as their production data. So now let's take a quick look at insider threat protections offered by CSPs. And again, I'm just going to show you one example here of insider threat protections available with a CSP just for context. So I'll switch to a browser, and I'm going to browse to compliance.microsoft.com, which is home of Microsoft Purview, which includes an array of compliance solutions. And here I see the Insider Risk Management solution. And when I go to the Policies tab here, I can create a policy to define what types of behavior I'd like to monitor for. And you'll see there are templates here that allow me to monitor for malicious behaviors like data theft, but also unintentional leakage, data leaks by my higher priority users or my habitually risky users. I see security policy violations, even misuse of health records. So a number of templates that get me off to a good start if I'm not quite sure what sorts of behaviors I want to monitor for. Now I'll quickly create a policy here just so we can look at the types of behaviors these policies will monitor for a bit more specifically. And when we get into the details here, I see I can look at the indicators. So for Office indicators, I can look at sharing behaviors. I can look at deleting of SharePoint files. As I scroll down here, I see adding users from outside the organization. I see removing sensitivity labels. And when I look at the CASB solution, I see unusual mass deletion. Another great example of tooling provided by the CSP that requires customer configuration. Continuing with the CSA egregious 11, we have metastructure and applistructure failures. These are vulnerabilities in the operational capabilities that CSPs make available, like APIs for accessing various cloud services. Now, if the CSP has inadequately secured these interfaces, any resulting solutions built on top of those services will inherit these weaknesses. Now, let's break these down just a bit further. The metastructure is the protocols and mechanisms that provide the interface between the cloud layers, enabling management and configuration. And applistructure are applications deployed in the cloud and the underlying application services used to build them. That would include PaaS features like message queues, functions, and message services. So who's responsible and how do we mitigate? Well, mitigating risks in this area is the responsibility of the CSP, so customers should verify the CSP has implemented their own secure software development lifecycle to ensure service continuity. And remembering that your CSPs generally don't allow direct audit, that's where we're going back to read assurance materials in which the CSPs tell us about their compliance with various audit standards and compliance standards. And rounding out the list, limited cloud usage visibility, which refers to when organizations experience a significant reduction in visibility over their information technology stack as a whole. Now, this is because in some models, the CSP owns the stack, so visibility is limited by design and by responsibility. And finally, abuse and nefarious use of cloud services. Now, while low cost and high scale of compute in the cloud is an advantage to enterprises, it's also an opportunity for attackers to execute disruptive attacks at scale. This makes executing DDoS and phishing attacks easier, so CSPs have to implement mitigating security controls to address these risks. Remember, CSPs are dealing with multi-tenancy at higher scale and with a more varied customer base than we are in a private cloud in a corporate environment. There are several approaches to risk mitigation in cloud environments, and the first of those is selecting a qualified CSP. The next is designing and architecting with security in mind. Security should be considered at every step, and that starts with the design process. The next risk mitigation tool is encryption, and data should be encrypted at rest and in transit. So that means storage and database encryption at rest, TLS and VPN for data in transit. And finally, ongoing monitoring and management to maintain security posture. Major CSPs generally provide tools to manage and monitor configuration security and to monitor changes to cloud services and to track their usage. So let's take a quick look at an example of this in a live cloud environment. Ongoing monitoring and management to maintain security posture. In fact, we call this capability Cloud Security Posture Management and Cloud Workload Protection. So I'm going to look on the Microsoft platform and Microsoft Azure at Defender for Cloud, which gives us that security posture management. AWS and Google Cloud Platform absolutely have equivalent tools. So here I can see my security posture. I can see recommendations coming from the CSP, and it even goes a bit further than that. So when I drill down into these recommendations, for example, encrypting data at rest, I see here it tells me I have a VM and a database. Now it tells me the status is completed. So if I had a regression, if somebody were to reverse a secure configuration, that would appear here as well, and a recommendation would be provided. And you can see that it's even been gamified to a certain degree. There's a score here in addition to that recommendation. So I'll go to security alerts, any alerts that require my attention, any configuration recommendations come up here. And going down the list under cloud security, I see that security posture. I see regulatory compliance. So this is going to show me some default configurations. Now this tool has dozens of compliance templates I can apply, but you see here SOC and ISO 27001 right out of the box. Here's that cloud workload protection. So any of my specific workloads are going to be surfaced here, so I can thumb through my VMs and then my PaaS services right here in one place. But just a quick look. So know that your cloud service providers have that capability baked in for you. And that brings us to section 3.4, Design and Plan Security Controls. Here we'll cover physical and environmental protection. This would include on-premises for private and hybrid cloud scenarios, system storage and communication protection, identification, authentication, and authorization in cloud environments, and audit mechanisms, functions like log collection, correlation, which would be a SIM function, and packet capture. We're going to touch on a few concepts related to physical and environmental protection, and in some cases revisit concepts we've touched on previously. But the primary consideration is site location, as that will have an impact on both physical and environmental protections. Your cloud data centers share many requirements with traditional co-location providers or individual corporate data centers, including the need to restrict physical access at multiple points, ensuring a clean and stable power supply, adequate utilities like water and sewer, adequate workforce. Remember for the exam that these considerations are a customer responsibility in on-premises or private cloud data centers and a CSP responsibility in the public cloud. I do expect overall to see less exam focus on physical considerations since it's a CSP area of responsibility for public cloud. We saw how to track down those CSP assertion documents that articulate the CSP's compliance with various regulatory and audit standards and frameworks. So site selection and facility design. The key elements in site selection and facility design include visibility, composition of the surrounding area, accessibility, effects of natural disasters. We don't want to build a data center in a site that's not easily accessible by automobile, for example, or that would have undue exposure to natural disasters. For example, I might not build a data center on the coast. Now, these are all problems for the CSP and the public cloud again. Customers need to focus on selecting CSP data center locations to meet their disaster recovery and data residency requirements. Remember, CSPs auto-select region pairs for redundancy, something to just bear in mind. So if we revisit the region pairs concept we talked about in a previous installment in the series, for example, we have East-West as a primary data center region. The CSP will pair a secondary region to serve as the backup, and that's generally 300 plus miles away, chosen by the CSP. So in my example, Microsoft uses West US as the region pair for East US. Moving on to system storage and communication protection, we'll touch on a few concepts you've seen at least once before. We want to make sure that we encrypt and protect data at rest, in transit, and in use, and protect systems and services from disruptive attacks at scale like denial of service and distributed denial of service, certainly made easier in the cloud. Boundary protections for ingress and egress, firewalls, intrusion detection and prevention, and key management, so protecting secrets of all kinds, passwords, keys, certificates, etc. That's really the technology half of the equation. And security practices, automation of configuration, think infrastructure as code. Responsibilities for protecting cloud systems and services should be well defined, monitoring and maintenance in place. This is a little more people and process focused. And remembering that customer and CSP roles in all of these areas are going to vary based on the shared responsibility model. So your responsibilities as a customer vary from IaaS to PaaS and SaaS, and we need to make sure you know the difference on exam day. And properly securing information systems can be a difficult task due to the sheer number of elements that make up a system. It can actually help to break these systems down into components and then apply security controls to make the overall task a bit more manageable, to kind of piece it out. Now, one source of controls is NIST Special Publication 800-53, Security and Privacy Controls for Information Systems and Organizations, which contains a family of controls specific to systems and communications. In fact, that control family includes more than 50 controls, many of which are relevant to system storage and communication. Now, to get a bit more specific, we'll break this down into policy and procedures, separation of system and user functionality, security function isolation, denial of service protection, boundary protection, and cryptographic key establishment and management. So starting with policy and procedures, we establish requirements for system protection and define the purpose, scope, roles, and responsibilities needed to achieve it. Separation of system and user functionality, essentially no single person can control all of the elements of a critical function or system. And separating user and admin functions can also prevent users from altering processes or misconfiguring systems, sometimes unintentionally. Security function isolation, separating security-specific functions from other roles, is just another flavor of separation of duties, really. Configuring data security controls like encryption and logging configuration would be perfect examples of that security function isolation. Denial of service protection. So denial of service is a disruptive attack at scale. It's definitely more difficult for smaller organizations to combat effectively, but most of your CSPs offer denial of service or DDoS mitigation as a service, and there are also dedicated third-party providers like Akamai and Cloudflare that offer DDoS mitigation protections. Now, in the big three, we have Azure DDoS, AWS Shield, and Google Cloud Armor, which are all DDoS mitigation as a service features. And on at least a couple of those platforms, they offer a basic tier of that service at no charge and requiring no real configuration. Then we have boundary protection, which deals with both ingress and egress protections, including preventing malicious traffic from entering the network, preventing malicious traffic from leaving the network, protecting against data loss, so data exfiltration, and configuring rules and policies in your routers, gateways, or firewalls. And your large CSPs generally have a policy engine that allows you to configure centralized policies to apply to your network virtual appliances, your virtual firewalls and gateways as you bring those devices or new regions online, so you don't have to configure those individual devices manually. So you're really codifying your configuration in infrastructure as code. And finally, cryptographic key establishment and management. So cryptography provides a number of security functions, including confidentiality, integrity, and non-repudiation, and it helps to match these functions to the protections they offer. So encryption tools like TLS or a VPN can be used to provide confidentiality. Hashing can be implemented to detect unintentional data modifications. That's really an integrity function. So if I hash a file, I calculate a hash, I send you the file, you calculate the hash on the file you receive. If the hashes match, we know the file has reached you intact. Its integrity remains intact. And additional security measures like digital signatures or hash-based message authentication code or HMAC can be used to detect intentional tampering. So HMAC can simultaneously verify both data integrity and message authenticity. So that's really a non-repudiation function. Let's move on to identification, authentication, and authorization. Authentication, sometimes abbreviated as Auth-N, is the process of proving that you are who you say you are. That's identity. Authorization, sometimes abbreviated Auth-Z, is the act of granting an authenticated party permission to do something. That's access. So permissions, rights, and privileges are granted to users based on their proven identity for resources to which they have been assigned access. And users should be granted minimum necessary permissions. This is called the principle of least privilege. I want to touch on accountability, which is a challenge with cloud identity. Users who perform activities on a system need to be held accountable for following policies and procedures. Accountability is typically enforced with adequate logging and monitoring of system activity. Now, cloud brings with it some challenges in enforcing accountability. For example, SaaS apps used as users travel make identifying anomalous or malicious behavior much more difficult. Bad password practices with our users, specifically users reusing passwords across services, is a problem, and the use of personal devices in BYOD or bring your own device scenarios. Now, modern identity as a service tools in the cloud provide solutions for these challenges, which we'll talk through and I'll show you a bit in just a moment. So let's start with multi-factor authentication, which works by requiring 2 or more of the following authentication methods. Something you know, like a PIN or a password, something you have, like a trusted device, or something you are, a biometric authentication. That second factor can be authenticator apps like the Microsoft Authenticator or Google Authenticator, a voice call, an SMS or text message, though SMS is considered a very weak second factor, and organizations like the Cloud Security Alliance have been recommending against that for some time. We have the Oath hardware token, which provides a time-based one-time password. And if that one-time password concept isn't crystal clear, think about any authenticator app you use. Microsoft, Google, OneLogin, any third party. They also generally serve as a software oath, providing that time-based one-time password in the form of a numeric sequence that changes every couple of minutes. Continuing with multi-factor authentication, so 2 or more authentication factors, obviously more secure than a single authentication factor. If you talk to some of the identity as a service providers, you might be surprised to learn that in the opinion of many experts, passwords are the weakest form of authentication. Now, password policies help increase their security by enforcing complexity and history requirements. Smart cards are a good option, which include a microprocessor and cryptographic certificates. Oath tokens are a stronger second factor option, creating a one-time password, whether that's a hardware token or a software token like the Authenticator app on your phone. Biometric methods, identifying users based on a fingerprint or facial recognition. Every modern iPhone features facial recognition. Your Android phones that don't offer facial ID do have fingerprint, generally speaking. So lots of options to go beyond a simple text message for that second factor. Now let's shift gears and talk about conditional authentication policies. This capability is increasingly common in identity as a service platforms. We've seen this in Azure Active Directory used with Office 365 for a lot of years now. So a conditional authentication policy will typically look at the signals around the authentication attempt, the user and their location, the device they're authenticating from. Is it a known device? Is it compliant with our security policies? Is the application an approved application? What is the real-time risk rating of this user? And typically that risk rating comes from machine learning and AI processing data from that user's past behaviors, potentially some user entity behavioral analysis that tell us if conditions are unusual, if risk is medium or high potentially. These signals will be processed together, and then the platform will allow access, block access, or potentially require multi-factor authentication. We can throw an additional prompt at that user if the conditions tell us that there's something a bit unusual. And if they meet the bar, then they are granted access to our data and resources. And this functionality works seamlessly with the Authenticator app on our mobile device that's ubiquitous today, the authentication application it's also called. So it's a software-based authenticator. It implements two-step verification services using the time-based one-time password algorithm and HMAC-based one-time password algorithm for authenticating users of software applications. That's the Authenticator app. And we know Microsoft Authenticator and Google Authenticator are really just 2 of many. But the Authenticator apps from companies like Microsoft and Google generate one-time passcodes using these open standards that are developed by the Initiative for Open Authentication, so OATH. You'll hear HMAC and TOTP tokens called OATH tokens with some of these providers, just different names for the same functionality. We have push notifications where the server is pushing down the authentication information to your mobile device. So you have notifications enabled on your phone, and really there's a finer grain of notifications. It's time-sensitive notifications, so that push notification will push a notification from your Authenticator app directly to you on your phone right away when you need to respond to that second factor. But the identity platform is using the mobile device app to be able to push that message to you in real time or near real time so you can respond to that second factor on your phone. Now I'd like to take just a minute and show you conditional authentication policies in an identity as a service platform, just to give you some real-world context for how that functionality increases the security around identity and access management in the cloud. So I'll switch to a browser here, and I'm looking at the Azure Active Directory Admin Center. So this is Microsoft's identity as a service platform. So if you've not used this with Microsoft Azure, maybe you used an Azure AD account with Office 365. This is the platform that supports Office 365 for identity. Now I'm going to scroll down and look at the security features of Azure Active Directory, and conditional access is what Microsoft calls their conditional authentication functionality that I was describing in the presentation. Now I'm going to look at an existing policy here. Exchange Online requires compliant device. So I can see it's already configured to look at some of the signals as part of that user's authentication attempt. So I can apply this policy to all users or specific groups of users, even guests and external users. I can apply this to specific applications. I can drill down to a specific app or apply it to all apps. Now let's look at conditions. So I see here I can act based on the user's location, and in fact I can exclude certain locations. So I might not want to apply additional factors of authentication to trusted locations. So it's certainly possible that when someone is on a compliant device in a trusted location, we're going to skip this policy and I'll just exclude them. And I can look at device platforms, so I can apply this to specific types of devices: Windows, Mac OS, iOS, Android, etc. None or low, maybe I want to apply these additional authentication conditions. Now I'll look at user risk. So this is the risk level for the user itself for that identity. And again, giving me the option to configure my tolerance there. Now I'll scroll down a bit and look at my access controls here, so I can configure some conditions around access. So I can choose to grant or block access. Now, blocking access is a pretty straightforward decision. I'm just checking block. But under grant, what you'll notice here is I can require MFA. I can require specific authentication strength, a compliant device, a device that's hybrid Azure AD joined, so joined to my on-premises Active Directory and synced to my identity provider in the cloud in Azure AD. I can require an approved client app and an app protection policy, which would be something we'd set up in our mobile device management platform. And then you'll notice down here, I can require one of these controls or all of these controls. So I have a lot of flexibility in the functionality, and on this platform, they actually offer the option to straight up enable that policy or to put it into report-only mode, which can be handy because we can assess what the impact of the policy would be before we roll it out to live users. So again, just a quick look. Hope that gives you some context. So back to our presentation, let's talk about federation, which is a collection of domains that have an established trust. So the level of trust may vary. It typically includes authentication and almost always includes authorization. We're typically using this for identity and access management. It often includes a number of organizations that have established trust for shared access to a set of resources. For example, you can federate your on-premises environment with your Azure Active Directory and use this federation for authentication and authorization. This sign-in method ensures that all user authentication occurs on-premises. We are federating to our on-premises directory. It allows administrators to implement more rigorous levels of access control. So historically, we would use federation so we could leverage certificate authentication or a key fob or a card token. Some of these methods are making their way into the identity as a service platform, so federation has become less necessary in some circumstances. I'd like to talk through a quick identity federation example I think might resonate with you. So I have a website, let's say it's hosted in Microsoft Azure, that's my CSP. So that's going to use Azure Active Directory as its identity as a service, that's Identity Provider A, IDPA, that's Identity Provider A. I have a user who wants to authenticate with identity provider B. Let's say they're a Facebook user, so they don't have an Azure Active Directory account, and I want to facilitate easy authentication of Facebook users to my website without requiring everyone to have an Azure AD account. So what I can do is configure federation. I can configure Azure Active Directory to trust Facebook as an identity provider. So identity provider A, Azure AD, trusts identity provider B, Facebook. And that way my user can authenticate with their Facebook account, and then they are granted shared access. Now, this may be cloud or it may be on-premises. We definitely see identity federation happening between identity providers in the cloud and on-premises, like Active Directory on-prem is quite common. And trust is not always bidirectional, as in this example, trust only happens in one direction. And incidentally, configuring Facebook as an identity provider in Azure Active Directory is not that difficult. In fact, I'm just going to go back to the portal quickly, and I'll click on external identities here just to show you all identity providers, and you'll notice Facebook is right there. So many of your identity as a service platforms are going to have similar functionality to allow Facebook, Google, Twitter as potential identity providers. And with identity and access management, audit mechanisms are top of mind. We need to collect logs so we have an audit trail, and your cloud services will offer different controls over what information is logged. What they will have in common is they collect a minimum level of security relevant events, like the use of privileged accounts or changes to privileged accounts. And a log aggregator, like a Security Information Event Management System, or SIEM, can ingest logs from all of your on-premises and cloud resources for review and correlation. So NIST SP 800-53 and the OWASP logging cheat sheet both offer guidance on specific information to capture in audit records. And good news there, we covered both of these in Domain 2 of this series. So correlation that I just mentioned refers to the ability to discover relationships between two or more events across logs. This capability is commonly associated with a SIEM, a Security Information Event Management System, which correlates events and logs from many sources. This is very important in investigation and incident management, security incidents, because we can correlate activities across a broad variety of sources to provide a more comprehensive picture of the actor's activities in our environment. We touched on some of the core tenets of a SIEM in Domain 2, and we'll talk about SIEMs in greater depth later in this series. And to round out 3.4, we'll touch on packet capture and replay. So packet capture tools are also called protocol analyzers. And in the cloud, some cloud environments may not provide any facility for capturing packets, particularly in SaaS scenarios where the customer is not responsible for anything related to the environment. Certainly, you'll see that your CSPs offer some facilities for IaaS and other foundational scenarios. Now, Wireshark is a free open source protocol analyzer. It has CLI and GUI versions, Windows and Linux versions. It is really ubiquitous. This is the de facto standard for packet capture. Now, some of your CSPs support Wireshark directly. Others have specialized services to perform packet capture on virtual networks. So two good examples. In Microsoft Azure, there is Network Watcher, which is a specialized packet capture medium. AWS supports Wireshark directly. Incidentally, Network Watcher in Azure produces PCAP output that we can open in Wireshark. So your CSP protocol analyzers can actually save the data that they collect to a Wireshark-compatible packet capture file, or PCAP, which is the case in Azure and a couple of other platforms that come immediately to mind. And that brings us to section 3.5, Planned Disaster Recovery and Business Continuity. So here we'll touch on business continuity and disaster recovery strategy. Business requirements. We're going to touch on three key acronyms: Recovery Time Objective, Recovery Point Objective, and Recovery Service Level. And creation, implementation, and testing of our business continuity and disaster recovery plans. A good place to start is by identifying the difference between a business continuity plan and a disaster recovery plan. So the BCP focuses more on the whole business, where the disaster recovery plan focuses more on the technical aspects of recovery. The business continuity plan will cover communications and process more broadly. Another way to think about that is the business continuity plan is an umbrella policy, and the disaster recovery plan is part of it. So what are the goals of DRP and BCP? Well, it's all about minimizing the effects of a disaster by improving responsiveness by the employees in different situations, erasing confusion by providing written procedures, and participation in drills to ensure folks know what they are doing in the event of an actual disaster, ultimately helping your important users executing the plan to make logical decisions during a crisis. There are a few core definitions related to business continuity planning that are worth knowing for exam day. So, the business resumption plan. This is the plan to move from the disaster recovery site back to your business environment, or back to normal operations, in other words. Mean time between failures. That's a determination of how long a piece of IT infrastructure will continue to work before it fails. Mean time to repair, or sometimes mean time to recovery, a time determination for how long it will take to get a piece of hardware or software repaired and back online. Max tolerable downtime, the amount of time we can be without the asset that is unavailable before we must declare a disaster and initiate our disaster recovery plan. So let's shift and talk about business continuity and disaster recovery strategy. I wanted to provide just a couple of definitions here that may come in handy on exam day. So the business continuity plan is the overall organizational plan for how to continue business after an event has occurred. It's a proactive risk mitigation strategy that contains likely scenarios that could affect the organization and guidance on how the organization should respond. In other words, the business continuity plan is going to focus on the most likely scenarios. This plan is sometimes called a continuity of operations plan. Now, depending on the sources you look at, some sources will define a difference, call out a subtle difference between a business continuity plan and a continuity of operations plan. If you look at the common body of knowledge for the CCSP exam, these two are considered one and the same. And then the disaster recovery plan, again, is the plan for recovering from an IT disaster and having the IT infrastructure back in operation. One is business focused, the other is more tech focused. And the business impact assessment, which we talked about earlier in this series, is used to determine which processes are critical and which are not. It measures the impact of specific systems and processes, and any that are deemed critical to the organization's functioning must be prioritized in an emergency situation. The business impact assessment contains typically a cost-benefit analysis and a calculation of the return on investment. And just pivoting to look at business continuity and disaster recovery from a CSP perspective, a cloud data center that's affected by a natural disaster will likely activate multiple BCPs and DRPs. A CSP will activate both plans to deal with the interruption to their service. Now, one key element of the BCP is communicating incident status to relevant parties. Now, the customer is responsible for determining how to recover in the case of a disaster in the cloud. So, recovery of our applications is not necessarily going to be automatic, and a customer may choose to implement backups or utilize multiple availability zones, load balancers, or other techniques. In other words, the CSP is going to give us the tools, but they're not necessarily going to do all of that design and implementation work for us. We have to use the tools we're given. CSPs can further protect customers by not allowing two availability zones within a single physical data center within a cloud region. Now, we talked about availability zones all the way back in Domain 1, so let's just briefly revisit the concept of availability zones in a cloud data center to refresh your memory here. So availability zones are unique physical locations within a region with independent power, network, and cooling. And they're comprised of one or more data centers. If we look at a region for a cloud service provider, like US East, for example, that region is going to consist of multiple data centers in fairly close proximity, and availability zones will provide a way for us to spread our infrastructure within that region, within those data centers, to tolerate data center failures via redundancy and isolation. The focus there is really on providing redundancy within that data center region. So if I put a load balancer in place with multiple web application instances, I would hope to spread those throughout the data centers in that region across availability zones. So I make my load balancer zone redundant, in other words. But the focus again is on data center failures within a region. So our hope is that our CSP doesn't provide availability zones that leave us stuck in a single data center. And your major CSPs have multiple data centers within a region, so it can be safely assumed this is true. So let's talk about the communication plan, the plan that details how relevant stakeholders will be informed in the event of an incident, like a security breach. It would include a plan to maintain confidentiality, such as encryption, to ensure that the event does not become public knowledge, at least before we're ready. The contact list should be maintained that includes stakeholders from government, police, customers, suppliers, and internal staff. Now, compliance regulations like GDPR include notification requirements, relevant parties, and timelines. For example, GDPR has a 72-hour time limit on the point by which certain notifications must go out. But confidentiality amongst internal stakeholders is desirable, so external stakeholders can be informed in accordance with the plan. You want to be the one, as an organization, informing your stakeholders, not allowing them to get that information from a news bulletin. So when we have an incident, there are multiple groups of relevant stakeholders that we need to inform and manage, and they may include internal stakeholders, a cyber insurance provider, business partners, customers, law enforcement. A stakeholder in this case is a party with an interest in an enterprise. Corporate stakeholders include investors, employees, customers, suppliers. Regulated industries like banking and healthcare will have requirements driven by the regulations governing their industries. So stakeholder management and communication plans will certainly be influenced by the industry that your organization works in. So let's talk business requirements. These are the three acronyms called out in the exam syllabus. There's the recovery point objective. That's the age of data that must be recovered from backup storage for normal operations to resume if a system or a network goes down. Next, we have the recovery time objective, or RTO, which is the duration of time and a service level within which a business process must be restored after a disaster in order to avoid unacceptable consequences associated with a break in continuity. SLAs between a company and its customers will definitely influence the RPO and the RTO. In fact, they will be determined based on contractual SLAs between a company and its customers, or operating level agreements, or OLAs, between the IT department and other departments within the organization. And finally, we have the recovery service level, which measures the compute resources needed to keep production environments running during a disaster. It is a percentage measure, 0 of 100, of how much computing power you will need during a disaster, and based upon a percentage of computing used by production environments versus other environments like development, test, and QA. So for example, if I have a 10 web server environment and 8 of those servers are used for dev, test, and QA, I'd only need to bring the 2 production servers into my DR environment. I'm only going to migrate what I need to keep the production trains running, so to speak. But that recovery service level answers the question, what needs to be migrated to keep production running? And another quick real-world look, this time at data backup and retention features in Platform as a Service offerings. This will only take a minute, but it'll be a good reminder of the pros and cons, the trade-offs in Platform as a Service. So I'm going to look at Azure SQL, so Microsoft's PaaS offering for SQL Server. So I'm looking at a SQL instance here, and I'll go down under data management to backups. And what I see down here are my available backups, but I'm going to look at my retention policies. And what I want to show you here is when I look at the retention policies for this server, we'll notice here that for PITR, which is point-in-time restore backups, I only have so many days that I can select there. There's a sliding scale that gives me 1 to 7 days, and I can then look at my differential backup frequencies. I have a drop down that gives me a limited number of options. I have a little more control in my long-term retention. You'll see here it mentions that I can keep my long-term backups for up to 10 years. So I have that long-term retention flexibility, but less flexibility in some of the short-term point-in-time recovery options. So the upside is configuration is very simple. It's just a few clicks. The downside is I have to accept the limitations that come with that platform as a service offering. Next up is BCDR, or Business Continuity and Disaster Recovery Plan Creation, Implementation, and Testing. And I'd like to talk through the process with you, beginning with the design phase. We design our BCDR plans based on priorities from the business impact analysis. And FEMA and InfraGard are organizations that can also advise us on likely disasters for a region, so we prioritize our planning around the most probable impacts. Then we implement our plan to protect critical business functions. Again, we're always focused on valuable assets, so when we're designing plans to recover business operations and infrastructure, we're focused on critical business functions first. We also need to identify key personnel, as they will be the ones carrying out these BCDR plans. Now, in the testing process, we're testing to make sure our plans function as expected and that the people involved know their roles and responsibilities and that the plans actually work. Testing both BCP and DRP plans is essential, and disaster recovery and business continuity plans that are not tested seldom work as expected in live use if we haven't tested and refined them first. And when we conduct these tests, we then report and revise. So our business continuity and disaster recovery plans should be revised as necessary based on test results. And test will definitely identify need for revision because our business evolves, and so these plans must evolve and be refined over time to continue to align with our critical business functions and processes. So let's talk through a few disaster recovery test scenarios. We need to test our business continuity and disaster recovery plans at least annually. Most organizations will test them in part in various forms more than once a year. Common disaster scenarios would include data breach, data loss, power outage or other utilities, network failure. So notice that not every impact is the most significant impact. We want to test a range of impacts. Natural disasters, civil unrest or terrorism, we're getting more serious now, and pandemics. And the plans should also test the most likely scenarios first, but can also be tested in a number of ways. So there are different types of tests we can carry out. So for example, tabletop testing. Members of the disaster recovery team gather in a large conference room and role play a disaster scenario. Usually the exact scenario is known only to the test moderator, who presents the details to the team at the meeting, so they are responding in the moment. The team members refer to the document and discuss the appropriate responses to that particular type of disaster. So a couple of benefits to this type of testing is that a tabletop test is role play only, so it's a minimal impact on productivity, and it's also a great way in your early revisions to identify revisions to the plan steps. When you write out that first draft of a disaster recovery or business continuity plan, nobody's going to get it perfect on the first draft, so the tabletop testing can help us refine the plan so we are ready for a real impact. Then there's a dry run. In this test, some of the response measures are tested on non-critical functions, so there's a bit of doing in this case. And then we have a full test, which involves actually shutting down operations at the primary site and shifting them to the disaster recovery site, when the entire organization takes part in an unscheduled, unannounced practice scenario of full business continuity and disaster recovery activities. And just a couple of notes on plan implementation. So implementing business continuity or disaster recovery processes may necessitate utilizing cloud computing for critical services. So customers can take advantage of the cloud's high availability features like multiple availability zones, automatic failover to backup regions, direct connection to a cloud service provider. And most of these choices come with costs that have to be considered. Even if we're talking about intra-region features like availability zones, protecting us against a data center failure, or if it's automatic failover to a backup region, when we're implementing that type of redundancy, there's going to be some infrastructure involved that has a subscription cost. But the cost of high availability in the cloud is generally less than a company trying to achieve high availability on their own. But it needs to be cost effective. At the end of the day, the cost of building resiliency should be less than the cost of business interruption. And congratulations, you've made it to the end of Domain 3 of the CCSP Exam Cram series. As always, I hope you're getting value from the series. If you have any questions, feel free to leave those in the comments section below this video or reach out on LinkedIn in a private chat. And I'll look forward to seeing you in Domain 4. So until next time, take care and stay safe.